Hi everyone. Okay, so before we start the lecture today, just want to make sure everybody's doing okay with your project, right? And feel free to contact me if you have any questions, concerns regarding our course project. Okay. Okay. So since some of you asked me to bring more exercise problems for the continuous time Markov chain, I decided to bring and extract a couple of problems from one of our textbooks, Introduction to Probability Models by Sheldon Ross. So today we are going to solve 3 of those problems, okay? And then next time I'm going to give you other exercise problems as well, okay? Okay, so here's the first problem. That is the exercise number 13 from chapter 6, end of chapter 6 problems. Okay. So let me read the problem description. A small barber shop operated by a single barber has room for at most 2 customers, and potential customers arrive at a Poisson rate of 3 per hour, and the successive service times are independent exponential random variables with mean 1/4 hour, which is 15 minutes, right? And we are going to answer for these 3 questions. First question, we want to know the average number of customers in the shop and the proportion of potential customers that enter the shop, and the barber, if the barber could work twice as fast, how much more business would he do? Okay, so first of all, as always, we're going to construct Markov chain model. Okay, so in order to do that, we need to define the state of system. So how do you define the state of system? So let me use smartboard. Okay, so go back to the problem description. I define the state of system as the number of customers, okay, at the barber shop. Does that make sense? Okay, and the barber shop is operated by a single barber, and it has only room for at most 2 customers. Okay, so if I define the state of system as the number of customers, the barber shop, then there will be at most 2 customers in this barber shop, right? So we're going to have 3 different states like this, right? And what is the arrival rate of the customer? Okay, the arrival rate is 3 people per hour, right? 3 per hour. So this is going to be 3 per hour. Same. If there is 1 customer, still the customers arrive 3 per hour. Now, how about the service rate then? It does say, okay, it provides the service times, right, instead of service rate. So the service time is mean 15 minutes, right? So what is the service hour? I'm sorry, the service rate. What is the service rate? 4 per hour, right? We just need to take the reciprocal of this. So it's going to be 4 per hour, right? That is the service rate. So we're going to put them in here. And since there is only one barber, right? So you would not multiply by 2. If there are 2 barbers, then you're going to multiply 2. So that if there are 2 customers, then both barbers will be busy, right? But this is not the case, right? Since there is only one barber, although there are 2 customers in the shop, here we're going to work on only one barber will work on the customer, okay? So you're going to multiply by 1. And then here as well, multiply by 1, since there is only one barber available. Sorry, it's very dry this morning. Okay, and now we are going to determine the steady-state probability distribution. And we know that this Markov chain model is a burst-test process, right? See, the number of customers in the shop has increased by 1 and decreased by 1. And customers' arrival and the service are independent each other. So obviously this is good example of a burst-test model, right? So we're going to use the streamlined version of the formula. That's going to be 1 plus first arrival rate over first service rate. And the product of first 2 arrival rate over the product of first 2 service rate, right? So 4 and 4. Is that right? So what is this? This is going to be 16. Denominator and numerator becomes 16. And then 4 times 3, 12, plus 3 times 3, 9, right? So what is this? Is that 37 over 16? Is that right? So pi 0 is 16 over 37. Because, yeah, be careful. You know, this cannot be the pi value, right? Pi 0. Because the probability cannot be greater than 1. So be careful. So once you get pi 0, we can easily determine other pi values. Pi 1 would be this, 3 over 4 times pi 0. And pi 2 is this, right? Which is 9 over 16 times pi 0. Is that right? So what is this? Three over 4, 16 over 37. This is 4. 12 over 37, right? How about this? 9, 16, 16, 37. So 9, 37. Is that right? Okay. Now, let's go back to the question. Okay. Our first question is the average number of customers in the shop. that's going to be easy. So how'd you get the average number of customers in the shop? If you are in state 0, then there is no customer, right? So 0 times pi 0. Likewise, plus, if you are in state 1, there is one customer. So 1 times pi 1. Of course, if you are in state 2, there are 2 customers. So 2 times 2 times pi 2. Okay? So what is this? This is 0 plus pi 1, 12 over 37, 2 times 9 over 37. What is this? 30 over 37. Okay? And I told you last time, the total number of customers in the entire system can be represented by capital R, right? So this is the average number of customers in the entire system. Okay, how about the next question? It asks you the proportion of potential customers that enter the shop. So how do you answer this? So let's go back to the transition diagram. Yeah. So if you are in state 0, then the customer arrives, right? If you are in state 1, again, customers arrive, right? But if there are 2 customers already in the shop, then nobody will be coming, right? Because they know that there is not enough room, right? So it does say this barber shop has room for at most 2 customers, right? Since there is no waiting rooms available, so there is no further customers arrive if there are 2 customers already in the shop, okay? So how do you answer for part B? The proportion of the potential customers enter the shop. This is very similar to one of the questions from last time. How do you answer that? Pi 0 plus pi 1. Or 1 minus pi 2. Same. Is that right? So what is this? What is this amount? Pi 0 is 16 over 37. Pi 1 is 12 over 37. So pi 0 plus pi 1 is 28 over 37. Okay? Does that make sense? Okay? So let me follow up this question. What if I ask you, what is the number of potential customers who enter the shop? Then how do you answer? So the number of customers who actually enter the shop. How'd you get this value? How'd you get this? If you are in state 0, this is the customer's arrival rate. If you are in state 1, this is the customer's arrival rate, right? So what you need is just multiply lambda to this value, right? 28 over 37. Lambda is, in our case, 3, right? So what is this number? Could you give me this number? It is 84 over 37. So it's going to be a little over 2 point something. 2 point? I'm sorry? 2.3? Okay. It's 2.3 approximately, of course, right? 2.3 customers per hour. So that's going to be the actual number of customers enter the system, enter the shop. Okay? Okay, now let's deal with the question C. If the barber could work twice as fast, how much more business would he do? Okay, so now we need to modify our transition diagram a little bit, right? So that the barber could work twice as fast. So now, what you need to do is, instead of 4, what do we have? 8, right? They can serve twice as many customers, right? Because he can work twice as fast. Is that right? And then based on that, you're going to recompute and determine steady state probability distribution like this. Okay? So let's do that. Okay? So this is the second case. So now we have 0, 1, 2. Customer arrival rate is same as before, but the service rate of the barber becomes 8 per hour. That's the changes, right? So we have 8 per hour. Now, steady state probability distribution can be obtained by 3 over 8 plus 3 times 3, 8 times 8, right? What is this? 64, and then 64 plus 24 plus 9, right? What is this? 88 plus 9, 97, right? So we have 97 over 64. So pi 0 now becomes 64 over 97. Is that right? And then pi 1 would be 3/8 times 64, 97. What is this? 24 over 97. Likewise, pi 2 would be 9 over 64, right? Times pi 0, 64 over 97, which is 9 over 97. Is that right? So, like we did before, referring to question B, At the moment, the proportion of customers who enter the shop becomes what? Same or pi 0 plus pi 1, right? What is this? 64 plus 24, which is 88 over 97. Is that right? So that's the proportion of customers who enter the system, who enter the shop. That's the proportion of customers who enter the shop, barber shop. Okay? Now, then, what is the actual number of potential customers who enter the shop? The number of customers enter the shop. Like we did earlier, up here, you just need to multiply by lambda, right? So lambda times this value, 88 over 97. What is this? Lambda is 3. So is that 264? Is that right? Over 97. So what is this? Could you give me this? A little less than 2.7. Okay, is it 2.7? Okay, thank you. So approximately 2.7 customers. Okay? Okay, so what is the question here? Okay, if the barber could work twice as fast, how much more business would he do? Now you should be able to answer this question because you already got all the required value to answer this question. So this is the actual number of customers who enter the shop. So as a barber, you need to work on this number of people. Is that right? Previously, how many people entered the shop? 2.3. So what you need is minus 2.3. Is that right? Does that make sense? So it's going to be 0.4 customers per hour, right? So the business he does, or the improve, actually is improved, right? Because he worked faster, right? Improved by 0.4 customers per hour. That's what I'm going to, what I would answer for this last question C. Does that make sense? Any questions? Okay, good. Then let's work on the second problem. So let me give you a couple of minutes. Why don't you read through the problem description? And then you can build up the transition diagram. Okay, so in this problem, potential customers arrive at a full service, one pump gas station at a approximate rate of 20 cars per hour. So this is the customer's arrival rate, right? 20 cars per hour. However, customers will only enter the station for gas if there are no more than 2 cars, including the one currently being attended to at the pump. And suppose the amount of time required to service a car is exponentially distributed with a mean of 5 minutes. Okay, so the service time is given as 5 minutes. Then what is the service rate? So how many 5 minutes are there within 60 minutes? 12, right? So that's going to be 1 over 12 hour. Is that right? This is the service hour. So you need to convert to service rate by taking the reciprocal of this. So service rate would be 12 per hour. Does that make sense? Okay. So we collected this information. So based on this given information, let's build up our transition diagram, Markov chain model. So again, let's use the state of system as the number of customers, number of cars at the gas station. Then we're going to have 0, 1, 2. Is that right? Customer will only enter the station for gas if there are at most 2 cars. Okay, at most 2 cars. It's no more than 2 cars means at most 2 cars, right? So if there are 2 customers in the gasoline station, then still the cars arrive. Is that right? Okay. So the arrival rate is 20 per cars, 20 per hours, sorry. And the service rate is 12 per hour. Is that right? So if there are 3 cars already in the gasoline station, then there will be no more cars arrive. Okay? So we're not going to include this, right? Okay. Now let's determine the steady state probability distribution. So 1 over pi 0 is equal to 1 plus 20 over 12. What is this? That's going to be 5 over 3, right? And then 5 over 3 square, 5 over 3 cube. Is that right? So what is this? 27, the denominator, and 27 and then 9 times 5 is 45. 3 times 25, 75, and then 125. Is that right? So what is this? It's going to be, this is 272 over 27. Is that right? So we know that pi 0 is 27 over 272. Is that right? Okay. And we know that pi 1 is 5 over 3 pi 0. Pi 2 is 25 over 9 pi 0, right? Pi 3 is 125 over 27 pi 0, right? So what is this? So this is 9 times 5, 45 over 272. Is that right? How about this? 3 times 25, so 125 over 272. How about this? $125, 272. Well, something is wrong. This is okay. Oh, this is wrong. Okay, this is not 125. All right. 3 times 25 is not 125. Is 75, right? So now 125, 75, 200, 27 plus 45, 227, 272. Okay, so now this is correct. Okay. Now let's go back to the question. Okay, it's been asking you what fraction of the attendance time will be spent serving cars. So we know that whenever there is a car at the gas station, we assume that the attendant is going to be busy to take care of the car. Okay? So the fraction of the attendance time spent servicing the cars is equal to what? The fraction of time that there are cars in the system, in the gasoline station. Does that make sense? Okay? So how'd you get it? In stage 0, there is no customer, right? Unless otherwise, there is always customers, right? So how do you answer? 1 minus pi 0, right? That's going to be the answer, right? So 1 minus pi 0. So 272 minus 27, what is this? 245, right? Over 272. Is that right? Maybe around 90%. Okay, something like that. Okay, now let's move on to the next question. What fraction of potential customers are lost? We already did very similar questions earlier, right? What fraction of potential customers are lost? When do you lose the customer? If there are 3 customers already, then you're going to lose all of the customer, right? So that's going to be just pi 3. Is that right? How much is that? 125 over 272 over here. So it's going to be a little bit less than 50%, right? Okay. So how do you feel? Are you getting comfortable? Okay. Okay, so here's the last question for today. So let me give you 2 minutes. Please read the problem description and try to build up Markov chain model, continuous time Markov chain model. Okay, so in this example, a service center consists of 2 servers. Okay, now we are dealing with 2 server problem, each working at an exponential rate of 2 services per hour. So this is the service rate. If customers arrive at a Poisson rate of 3 per hour, so this is the arrival rate, then assuming a system capacity of at most 3 customers. Okay. So did you collect all of this information? So using this, let's work on Markov chain modeling. So again, if we define the system, the state of system, as the number of customers, then the system capacity is 3, right? So we have 3 customer case as well. And then customer arrives, that's 3 per hour, right? 3 per hour all the way, right? What about the service rate? Service rate is 2 per hour, right? So it's going to be 2 per hour. But here, we got to be careful. It does say, this service center consists of 2 servers, each working the exponential rate of 2 services per hour. So, if there are 3 customers, then both of servers will be busy, right? So you need to multiply by 2. Of course, if there are 2 customers, both of servers will get busy, right? However, if there is 1 customer, then only 1 server will be busy, right? Probably the other server is in standby. So this is the complete transition diagram based on our the problem description. Is that right? Okay, now based on this transition diagram, let's build up. Let's determine the steady state probability distribution. Of course, this is another example of birth-death process, right? because number of customers increase by 1, decrease by 1. Customer arrival and service are independent each other. So we should be able to use this formula, right, for determining steady state probability distribution. 3 over 2 plus 3 times 3, 2 times 4, right? 3 times 3 times 3, 2 times 4 times 4. Is that right? So what is this? Denominator becomes 32. 32 plus 16 times 3, which is 48. 4 times 9. Sorry. 36, right? $36 plus 27. So how much is that? Okay, 70, 80, 116, 30. So 143, right? 32. So pi 0 becomes 32 over 143. Is that right? And then we know that pi 1 is 3 over 2 pi 0. Pi 2 is 9 over 8 pi 0. Pi 3 is 27 over 32 pi 0, right? So how much is that? So it's going to be 16 times 3, 48 over 143, right? How about this? 36 over 143. How about this? 27 over 143. Is that right? So we got all the pi values. Okay, so what is the question? Okay, the first question is, what fraction of potential customers enter the system? So this is very similar questions, right? What fraction of potential customers enter the system? Only if there are 3 customers already, then you're going to lose the customer, right? So it's going to be 1 minus pi 3, right? Make sense? So we can answer for question A is 1 minus pi 3. What is this? So that's going to be 116, right? Over 143. So what is this? Can you give me the number? 0.7, I don't know, 0.8 something? 0.8? Okay, approximately 0.8. Okay. How about question B? Okay, what would the value of part A be if there was only a single server and his rate was twice as fast? Okay, kindly, the problem provides you the new service rate. Mu becomes 4 per hour, Okay? So what you need is, instead of 2, 4, 4, you're going to have 4 all the way, because there is one server at the moment. Okay? But here we're going to work twice as fast as before. Okay? So let's draw the new transition diagram. So this time, same. Customer arrival rate, so 3 per hour. But the service rate becomes 4. And since there is only one server, you would not multiply by 2 here, right? Okay. So now let's recompute pi 0, pi 1, pi 2, and pi 3. So in this case, 1 over 3/4, 3 times 3, 4 times 4, 3 times 3 times 3, 4 times 4 times 4. What is this? Denominator becomes 64, 64 plus 3 times 16. So 48. 9 times 4, 36. And then 27. So how much is that? I'm sorry? 175. Thank you. And 64. Now, pi 0 becomes 64 over 175. Or is it the same? No? Okay, it's not. Okay. Previously it was 32 over 143. Now pi 0 becomes 64 over 175. Okay. So pi 1, actually we don't need to compute pi 1, right? We just need to compute pi 3. So what is pi 3? 27 over 64. Pi 0. What is this? 27 over 175. How much is that? Mm-hmm. 0.15? 4. Okay. So approximately like this? Okay. And the question is, okay, what would be the value of part A? There is a fraction of potential customers that enter the system. So, as we did earlier, 1 minus pi is 3. That's what you need to get. So what is 1 minus pi 3? It's going to be 0.8 4 6 something. Is that right? Okay. So there is a small increase compared to the previous case. Is that correct? So by changing the server and their service rate, you're going to expect different system behavior like this. Okay? Okay, so this is all for today. Like I mentioned earlier, today, next time I'm going to bring more example problems. I already identified a couple of problems from the Sheldon Russ, the Introduction to Probability Model textbook. So I'm going to work on that this coming Thursday. Okay? And then next week is yours. Okay? Be sure you're going to turn in everything by Sunday evening. Okay? So that you're going to be arbitrarily assigned for the presentation. Okay? Either Tuesday or Thursday. Okay? Okay, thank you. See you next time.